Okay. Okay, let's start. Welcome everyone. Good evening. It's a great pleasure to welcome you to the 33rd Vienna Circle lecture. And it's a great pleasure to welcome Lydia Patton as this year's speaker. Let me just say, before I say something about Lydia, let me just mention that this is a series of lectures that has a long history. I mean, it's the 33rd talk this year, and the lecture series was started. The first talk was in 1993 with Sol Kripke as the first speaker in this series, and in the last 30 years we had different scholars such as Michael Friedman, Anton Zeilinger, Helen Longino, Juliet Floyd, and more recently Flavia Padovani as speakers. And it's really a great honor to welcome Lydia Patton to give this talk today. Let me just mention a couple of points about Lydia's work. Lydia is a professor at Virginia Tech, and mainly works in philosophy of logic, philosophy of mathematics, but also in the history of philosophy of science, so in HOPOS, as well as in philosophy of physics. Let me mention three volumes that Lydia Patton has published as editor. This is a recent book, edited volume, published in 2023 on solutions in fluid dynamics and astrophysics, together with Eric Curiel from the MCP Munich. And then in 2018, the book edited volume Laws of Nature, and some years earlier, 2014, the Routledge book Philosophy, Science and History. Lydia Patton has published numerous articles on different topics in philosophy of science and in HOPOS, including articles on, let me mention just a few topics. Hilbert, neo-Kantianism, Cassirer, Thomas Kuhn's work, Rudolf Carnap's work, and the syntactic view of theories, or received view of theories, and then more generally and more recently, theory testing in physics and in general relativity, and so on and so on. The talk today will be on testing scientific theories. Lydia, it's a great honor.
Thank you so much. Thank you very much. And I'm so grateful for the opportunity to be here and to give this talk. And I want to really thank Georg Schiemer and Moritz Bodner and everyone who's been organizing the conference. It's been such a fabulous conference so far. And I'm really looking forward to concluding tomorrow. Although I wish we didn't have to conclude, we could just keep going with more neo-Kantianism. That would be fabulous. But we can do that, just not here. Okay, so what I'm going to be talking about today is my most recent view, and I think what I really think about theory testing. I've been developing this over some time, and so I'm going to present it. What I'm going to present is the outline, a broad sketch of what I'm thinking of as a coherent or united view of theory testing. But I'm also going to mention, since this is the theme, I am going to mention how it relates and how it can be built up, how my view can be built up with resources from the Marburg School, since that is the law, and also with more recent philosophy of science, including the idea of generalized frameworks. I'm going to talk about two very specific cases from the history of science one from the history of science and one contemporary actually, that I see as exemplifying the view, and then I'll conclude by sort of drawing some concluding remarks about where I see the theory going. So that's the basic idea behind what I'm going to be doing. But if this is going to be a lot, and the basic idea behind it is these first couple of slides where I'm talking about theory testing, And so that's really the way to, kind of the way into everything that I'm going to be saying, is this notion of theory testing that I'm about to present. Okay, so what I want to say is that there are, in fact, at least in my analysis for these purposes, two distinct parts of theory testing. And I use the word part because I don't mean that these are necessarily one after the other, right? So this isn't necessarily temporal, it's just that there are two elements or parts of theory testing that I want to emphasize. And what I want to say is that we usually focus on the first one, especially in philosophy of science, and I want to really emphasize the second one. So the first element of theory testing is the classic account of deriving hypotheses from a theory and gathering observations, so the deductive nomological model, Popper's severe testing. My colleague Deborah Mayo has picked up on this, right? The idea of taking a law, deriving predictions from it, and then testing it in experience and finding instances or counter instances. But the second part, oh, I got rid of the second part. Let me just quickly say, the second part of theory testing, though, is less often discussed in the philosophy of science. And this is the part where you already have the data. So this is the part where you've already done this experiment, the data is already in, and what you want to do is to figure out whether the data is actually consistent with the theory. So whether the data that you have is consistent with whatever hypothesis or whatever theoretical framework or formal claim that you are testing. Okay, so that's the second part. And this is the part that I think is sometimes not as much paid attention to in accounts of theory testing, is the second part where we have the data and we want to see whether they're consistent with the theory. So what we do have that's often considered, that is really a part of this, but that people often consider to be kind of separate from testing, or they name in a way that is separate from testing, is what's sometimes called post-data analysis in contemporary science, right? So you hear a lot about Bayesian testing, statistical analysis of scientific data, and this is obviously, you know, a key part, a crucial part of establishing a scientific result, right? So if you look into like CERN or LIGO or any of the major scientific projects, once you get the data in, you're going to do testing to figure out whether that data confirms your hypothesis or not, right? And so this this stage in research is often called post-data analysis. It's a statistical analysis that evaluates the strength of a result with respect to a set of hypotheses, claims, or parameters. This is when you hear about a 5 sigma, I'm being very general here, but 5 sigma results are those that have passed a stringent test. Severe tests from Popper and from frequentism, and also confidence intervals in Bayesianism are examples of post-data analysis. So here's a specific example. In gravitational wave astrophysics, post-data analysis results in a list of parameters of the source of a signal. So the signal that we're looking at is usually a pair of merging black holes or neutron stars or some merging astrophysical objects. And so then what we're going to do is look at the data that we get and analyze it to see what it tells us about the parameters of the source system, right? So these parameters might be mass, which would be an intrinsic property of the system, or something like how fast the two masses are orbiting each other, how fast the two stars are orbiting each other, or they might be extrinsic parameters like how far they are away from us, right? And so what you see in post-data analysis is often going to be something like in this famous paper. So this is the first paper. This is Properties of the Binary Black Hole Merger GW15914, which was the first LIGO detection of a black hole. And this paper, on one of the first pages of this report, which was a report of the first experimental detection of gravitational waves, you see this, which is actually relatively simple. So this is, This is a list of parameters determined by Bayesian inference that are within a certain confidence interval, right? So you can see, for instance, at the top, the total mass is 70.3. Under one model, it's +5 or -4, right? So it could be 75 or it could be 66, right? Solar masses, right? None of this, none of this matters to this talk, except in the sense that what happened to get this chart was that they got a bunch of data and they did a bunch of statistical analysis and they figured out, right, this data tells us that this system has these parameters within plus or minus so much, right? So this is usually the way we consider that second step of theory testing, is that the first step is we get the data, and then the second step is we do the statistical analysis to see whether the data actually fits with the theory. What I want to argue for is that the second step actually goes beyond statistical analysis, that our account of the second step of theory testing, where we look at whether and to what extent the data, the scientific facts that we get, the results that we get, fit with the theory, should go well beyond statistical analysis of the data to see whether it fits a certain hypothesis, right? So to make these kinds of estimates. So scientists have an excellent handle on how to calculate a confidence interval like what was done in the last slide, given a data set. And we might imagine that such calculations exhaust what I've called the second part of theory testing, when we have the data in and we want to see whether it's consistent with the theory or not. Okay, so we might say, you want to do the what I've called the second part of theory testing. All you got to do is crunch the numbers, do the calculations, and figure out, like, what are the properties of this system within plus or minus what, right? And then you publish your paper, and then you go on and get your grant or whatever it is that you want to do, right? What I want to argue is that scientists do more than calculate in the second part of theory testing, and that to understand the development of scientific theories in response to new evidence or even to existing evidence, it's necessary to understand how scientists respond to novel observations, okay? So how they take observations and compare them with theories and see whether they're consistent with them or to what extent they might constitute an anomaly for that theory. Okay, so the kind of stepping back, the basic idea behind what I want to say is that this second step, when you already have the data, you already have the results of your experiment, it goes deeper than just making statistical calculations. You can also say something more about what those scientific results say about the theory itself and about the theoretical framework that you're looking at. So, in order to get this off the ground, I want to look at two existing accounts of how this will work. So what I want to argue is that these two existing accounts are actually different examples of what I am talking about, of this, what I've called the second step of testing. Now, I want to be really clear. Neither of the people that I'm going to talk about, neither the Marburg tradition nor Adam Koberinski, who I'm going to talk about, would necessarily refer to what they're doing as any part of theory testing. But what I want to argue is that if we want a coherent or unified account of how to test scientific theories, we need to talk about how to look at results, data, evidence, and see how it fits in with the theory, and that step is really important in understanding how scientists respond to novel data. Okay, before I go on, is that much? We're good? Okay, good. All right, so the first thing I'll look at is the Marburg School. I am not going to go into very much detail. This is going to be the least competent Marburg paper today, but I am going to talk about some of the ways in which this account, I think, it really says something profound about how this second step of testing could be developed. So first, obviously, Hermann Cohen's and Ernst Cassirer's transcendental method begins with scientific facts and clarifies the conditions for establishing those facts. And to date, scholarship on their contributions focuses heavily on mathematical principles for obvious and sufficient reasons, right? This is something that is right. And I want to refer to Marco Giovanelli's recent paper in HOPOS, Relativity Theory as a Theory of Principles, and this is a reading of Cassirer's Einstein book. And this is an excellent paper in, of course, the best journal that there is. And so in this paper, Giovanelli argues that Ernst Cassirer presents relativity theory as a physics of principles, right? So the last manifestation of the tradition of the physics of principles. And he points out, by regarding Leibniz's scientific work as part of the prehistory of Kant's a priori, Cassirer, ultimately following Cohen, could clarify the latter concept of the a priori. Certain statements are not considered a priori because of their origin, because they're part of the structure of the mind or derived from the table of categories. They're a priori because of their role as a condition of the possibility of the mathematical science of nature. So here, this is a well-known fact about the a priori in neo-Kantianism. This isn't an absolute a priori that is considered as some kind of universal law of the mind, but rather these are principles that are considered as immanent, what Cohen referred to as the immanent foundations of science, because they have a role in deriving the results of mathematical natural science, right, and especially of physical science. So in this form, Cassirer argued more or less explicitly that Kant's combination of the a priori and the transcendental maintains its validity for the philosophical assessment of modern science. And part of the idea, I don't mean to just be, part of the idea then is that the principles of physics, the principles of mathematical natural science, gain their validity not just from being sort of universal laws or something like that, but from being that which we derive the results of science from, right? Okay, and here Giovanelli cites from Cassirer's notes for a series of lectures on relativity that were given at Hamburg in 1920 and 1921. And here he just talks about the Einstein's combination of the principle of the light principle and the relativity principle, and that this proves to be suitable to give a complete account of mechanical and optico-electrical phenomena, so much that's the result of relativity theory. In their connection, the two principles no longer represent a unified thing that exists in nature, but they formulate a uniform basic relation which all special laws of nature obey, a most general moment of our knowledge of nature. So here, I just want to focus on a small part of this fascinating group of issues, which is just that there are two steps that happen here. The first is that we identify the principles that have a Leistung, right, have a role to play in the derivation of the results of science. And then we recognize them as more general potential constraints on building further systems, further scientific systems and in further scientific reasoning, right? So that then we can formulate this as a constraint and say that, for instance, all future theories must obey the principle of conservation of energy, and if they don't, then we've found out something fundamental or interesting about those theories. And this is just from Cassirer's relativity book. These principles create the framework for the form of natural law in general, and this is truly uniform, although it's precisely through it that it's required that the particular space and time values that are determined within different systems don't agree, but only stay in a determinate functional relationship and in mutual coordination. And here, Cassirer says the most fundamental principle that the theory of relativity obeys is this principle of general covariance. So here, what we're doing is we're taking the results of relativity theory and looking at what is at the bottom of these results. This is just the basis of the Marburg view in a way, or of Cassirer's view of principles. We're looking at the basis of these scientific results in fundamental principles. Now, as is well known, extremely well known in work on the Marburg School, there are two ways to think about mathematics, the mathematics of natural science and about principles. One is as unrevisable eternal truths, and the second, and this is not what's up here, I do know that, is as dynamical principles. So this is the account usually given by scholars like Michael Friedman, who've talked about the dynamics of reason and the revisable a priori. I want to make a slightly different point. So I want to say that when we move from the idea of mathematical principles as unrevisable eternal truths or necessary in laws of nature, we can also contrast them with the best way to logically clarify structural relationships, both within a theory and between the theory and the phenomena. And I actually see this as an equivalently valid way to look at least Cassirer's view, and I'm happy, I expect to be challenged on this potentially, but I see this as one way to look at the Marburg position on the principles of natural science, at least in Cassirer. Is that what we want to do is look at how the structural relationships within a theory are derived from principles and how those principles constrain the relationship between the internal relationships within a theory and the relationship between that theory and the phenomena. And similarly, we can identify principles as part of two types of system: the logical mathematical principles that ground specific inferences in science, so those that are embedded in particular scientific results or that we can derive particular scientific results from. And secondly, the system of principles and concepts that allow for the construction of more generalized theoretical frameworks, right? So when we, remember, there was this movement that I just noted where when we find a principle for a particular physical result, sometimes what we have also identified is a potential condition or constraint on further similar theories, right? So the principle of conservation of energy works in this way, the principle of continuity works in this way, general covariance, Einstein argues repeatedly, works in this way, the principle of relativity, the light principle, and so on and so forth, right? So sometimes when we discover a principle, it's not just immanent in or embedded in a particular theory or result, but it's something that can have a more general application, or that at least we can apply in a heuristic way to say, well, look, let's assume that further theories might have this kind of structure, and if they don't, then that's going to be something interesting to learn about them. Okay, and we saw today from Francesca Biagioli's talk and from her earlier book, Space, Number, and Geometry from Helmholtz to Cassirer, and I'm going to talk about this again later. The process of measurement, of measuring physical quantities and coming to some physical result, might require us to broaden our symbolic framework, as when the problem of measuring space pushes us toward non-Euclidean geometry, and this might allow us to also discover more general principles. Okay, so I want to skip that. Here's the thing. Here is where I am going to, remember when I said that this is going to be the least, the least good talk on the Marburg School today. What I am going to do is shamelessly move from that very general sketch of the way principles might be used to determine more general frameworks, and then start looking at a similar account in more recent philosophy of science, and talk about the way that we might build general frameworks in theory testing over time. Okay, and so the Marburg School is going to be one example of this, but I'm going to make this much more general, and I am no longer going to make any claim to be even remotely historically accurate in the, in presenting this like anything like the Marburg view. Okay, so I want to be really clear about that, because what I'm going to move to right now is going to be something very much more general. Okay, however, it is going to sound familiar. I will say this. Okay, so what if we were to extend something like the Marburg account to more general frameworks that relate theories to the phenomena in general, and perhaps even to multiple possible ways that the world could appear to us as observers. So where we look at ways in which, if we change the principles of science, if we change the theoretical frameworks that we're looking at, if we analyze those theoretical frameworks, we can find multiple ways that those frameworks might be related to the phenomena. Here, there is a number of related accounts in contemporary philosophy of science. So Adam Koberinski's generalized frameworks, which I'm going to talk about in a minute, Laura Ritchie's modal resourcefulness in her book Interpreting Quantum Theories, Eric Curiel's generic structures in his paper Schematizing the Observer, my heuristic structural reasoning in the book that Georg mentioned on fluid dynamics, David Wallace's math-first structural realism, and Kerry Mackenzie's assertion that Cassirer is an early version of math-first structural realism, which is interesting, could all provide resources for extending something like this account. So to be clear, this account is the use of principles to build more general frameworks for theoretical analysis. In what follows, I'll focus on Koberinski's account, and then I'll explain mine. Okay. So this is from Adam Koberinski's paper, Generalized Frameworks in European Journal for Philosophy of Science. And so this is really kind of the basis for what I'm going to be talking about, partly because, in fact, not that long ago, at a conference, we were talking about how our approaches are kind of similar, and so this is something that I want to put forward and then explain what I want to do. So, in this modern era of frontier physics, we're seeing early stages of theory construction, using a method that I, Koberinski, call framework generalization. Roughly speaking, a framework generalization starts with a well-established theoretical framework for known physics. So here we start with a physical theory or a set of scientific results that we already have. Okay. What do we do next? We make explicit the core principles, assumptions, and relations implicit in this framework, and generalize a subset to create a generalized phenomenological model space. So you take what you do, you take these results, and you do immanent analysis, right? You look at what is implicit in this framework, what are the principles that we can find within this theory that make these results possible, right? What are the conditions for these results? And then we create a generalized phenomenological model space, meaning we look at multiple different ways that the world could be given that the world could appear, or that we could make observations, given this theoretical framework, okay, given this sort of generalized theoretical framework. This phenomenological space serves as an arena for turning precision measurements of quantities predicted by known theory into constraints on the allowed regions of theory space. So, this is fairly key, so I want to make sure that I get this. Instead of just saying, let's take principles like the principle of relativity and the light principle and conservation of energy and so forth, and using them as constraints on theory construction, we take that account and we blow it up to more of the elements of the theory, right? We look at a theoretical framework, we look at what's necessary in order to derive results from that theory, we generalize it, and then we say, let's use a bunch of these different elements of the theory as constraints on the way that we can conduct scientific investigation, okay, and the way that the phenomena can appear to us. This effectively allows for a comparison of known physics with a wide range of possible competitors without having to have explicit competitors in hand. What might this mean? We might see that we have a result already that tells us that the value of a variable is between x and x plus 10, right? And then we might, this is just a completely speculative example, right? And then we might think, well, but if we varied this quantity in the theory, then it might be that x plus 10 to x plus 20 is also physically meaningful. Like we could theoretically observe something within that range. We haven't yet, but we could look for it, right? Because if we varied this part of the theory, then that's what we would see. Okay. And so the idea behind a generalized framework is that we take more than the principles. We also take variables, constants, means of observation, measurement processes, and so forth, and we generalize them so that we see what are other ways that we might hook up this theory with the world in order to make observations that would test the theory. Okay. This is, let me stop here just for a second. With me so far? Ish? Okay. All right, so a couple of terms, and then I'm going to explain this, this account a bit more. So a couple of technological terms. Dynamical models in physics are more like theories. So this is going to be something like the model that you get from an equation. So these are going to be sort of basic physical models, right? So something like Hooke's law or just basic physical equations. Phenomenological models are going to resemble Morgan and Morrison's models as mediators between theory and observation. So they're ways to make some kind of theoretical concept observable, right? So Reichenbach also talked about this. A theoretical framework is the network of principles, symmetries, and constraints, usually mathematized into a formalism that gives us the common language of a given research program. So this is from the Generalized Framework paper. Okay, so these are just terms that are going to be used in what follows, and so I just wanted to clarify those a bit. Okay, so this is again from Koberinski's paper. Framework generalization is a theory construction method that starts with a well-established theoretical framework. And again, first you elucidate the core principles, constraints, and formalism, and determine their impact on some phenomenological domain. So the first thing that's really important is that this is usually something that's implicit in most theoretical results. And this is, again, this is kind of the key point that I wanted to take from the Marburg School, is that when you get a scientific result, it's often the case that what's implicit in that result is that you made use of certain theoretical resources, right? You made use of the formalism, the principles, the constraints, the variables, and so forth. It wasn't just that you derived it from some law. There were a bunch of theoretical resources, some of which are quite implicit, that you drew on to get that result. And what you do first in the process of framework generalization is make those explicit. Next, some subset of the core principles and constraints are generalized or removed, leading to an enlarged modal space of phenomenological possibilities. What does that mean? You take what it took to get the result that you've got, the observation you have, the experiment that you just did, or whatever, and you generalize it. So first you make explicit what it took to get the result that you have, and then you make that framework more general by simply enlarging the space of possible results that you could derive within that theory. And usually there are tons and tons of ways of doing this. I'm going to give a couple of examples. But there are lots of ways of carrying out this kind of procedure. But the idea behind it is you don't just do this through the principles, you do it through all of these different theoretical resources that you use to derive some kind of result in science. Okay. So this is a table from Koberinski's paper where he talks about the difference between a theoretical framework, a generalized framework, and the phenomenological possibility space. So this is from the paper on generalized frameworks. So a theoretical framework might be the quantum theory. And I actually just talked to someone on Tuesday who's working on these generalized probabilistic theories. So a generalized probabilistic theory is a generalized framework for the quantum theory that allows for multiple possible theories that include the quantum theory as one case. Right, or the current quantum theory is one possible case. So generalized probabilistic theories allow for the quantum theory, but then that there are other possible probabilistic theories that are in that possibility space. What is interesting, and I think what is particularly interesting from a neo-Kantian perspective in many ways, is that then you recognize, oh, if you do that, you are also determining a broader phenomenological possibility space. So more ways that the world could appear, more observations that you could possibly make, more phenomenological models that you could construct using this generalized framework. Okay, so generalizing the theory also makes your phenomenological possibility space broader. Okay. This, I think, is a fundamental point that I really, like, independently of all of the details of this, what I take from this is something that I fundamentally believe, which is that making the theory richer makes what we can observe richer. Okay, so everything I've just said is basically just that. If the more you put into the theory, the more the possibilities you build into your theory, the richer you make your theory, the richer you make your phenomenological possibility space, the more things you can observe, the more your observations can be meaningful. And this is explained here in 3 different cases: quantum theory, gravity, and particle physics, but we already went through one of the key ones for contemporary. So the first thing that's important about framework generalization then is that enriching your theory, enriching your theoretical framework and making it more general and broadening your space of possibility, allows experimentalists to search for deviations from the original theoretical framework within this enlarged phenomenological modal space. In other words, if you enlarge the space of possibilities allowed within your theoretical framework, you can do broader tests. You can test for more things, right? Which is helpful. Okay. We were eventually going to get back to testing, right? So the idea here is, it's often assumed that the best way to come up with a broader or more severe test of a theory is to come up with a better experimental method, and often that is true. But one way to do it is actually to come up with a different theoretical possibility, right? With a different theoretical framework that allows for more possibilities, for more observations to be made that might either confirm or falsify the theory, or that might at least serve as evidence for or against the theory. Okay. Statistically significant deviations from expected phenomenology indicate anomalies requiring revisions to the old framework or eventually new dynamical models. Okay. So Koberinski's initial motivation for the generalized frameworks account, which I hope I've explained adequately, but if not, we've got a lot of discussion time, is to show how frontier science develops over time. So frontier science for him is like new science that's pushing the boundaries, right? And to capture a crucial element of scientific progress. Now, building a generalized framework allows scientists to detect anomalies for a theory without first defining them explicitly necessarily, right? So you just build these more general frameworks and you're able to test for like general departures from theory assumptions, right? And you clarify the structure of the theory and you understand the theory better. Generalized frameworks widen the phenomenological possibility space without having to specify exactly what those phenomena will be, right? So you don't have to like predict what some new phenomenon will be exactly, but you can just say, well, look, it'll be somewhere within this range because this is what the theory tells us that it will be. But we don't know exactly what it is, if it exists. So Alan Franklin has a great book about this called The Rise and Fall of the Fifth Force, about the search for the fifth force. I think they've actually renewed the search for the fifth force recently. But there was a long search for a fifth force a while ago. And even though there wasn't any sort of specific new evidence for it, they knew exactly what it would look like because they did this kind of reasoning ahead of time, right? They said a fifth force would be this and this and this, and it would have these criteria and these characteristics because they did this kind of theoretical analysis ahead of time, right? Okay, so the thing is that this kind of reasoning sounds incredibly complicated, right? It sounds like you would have to do this kind of very high level, like analyzing the quantum theory or whatever. But this can be very simple. This kind of reasoning that I'm talking about can be incredibly simple. And it can amount to allowing for quite nearby possibilities. And so if you'll allow me, I'm going to present one of my favorite examples from the history of science. Some of you may know this already. Karl Jansky and radio astronomy. So if you already know the punchline, then that's good. But this is Jansky next to the telescope that he built, which we'll see about in a second. So this telescope, this is a picture from the NSF. So Jansky was an engineer at Bell Labs. That was one of his first jobs. He was an engineer at Bell Labs, and he was given an assignment to study intermittent static sources that might be interfering with radio waves used for transatlantic telephone calls. Okay, so basically his first task was at Bell Labs was to find the source of interference on a telephone line. It was a challenging assignment. He had to design and build special instruments for the purpose, most notably a large directional antenna system mounted on a motor-driven turntable that rotated 360 degrees about a central vertical axis riding on a circular track on the wheels of a Model T Ford. Okay. It was dubbed Jansky's merry-go-round. So this is from the American Physical Society website, and this is it. So he built this in the backyard of Bell Labs. This is the coolest thing ever. Yeah, this is great. Okay, but you can see the part where it can turn around. And that's important because you can tune the antenna that way, right? So you can turn the antenna around. Okay, so Jansky knew that there were certain sources of static on these phone lines that included local and distant thunderstorms, and he had a whole list of potential sources of interference on the telephone lines, and he ruled them all out. And once he analyzed all the data, so he got all of this initial data about the sources of interference, and he analyzed all of the data. So this is, you know, what I've referred to as kind of the standard account of testing, right? You get the data, you analyze the data. So he did all of that, and he ruled out every terrestrial source of interference on the telephone lines. And so you can probably guess, he said, what if it's not terrestrial? And in fact, it turned out that what he had done was build the first radio astronomy telescope. And that what he was picking up was coming from the center of the Milky Way. And so he is now known as the father of radio astronomy because he did a good job at his job as an engineer at Bell Labs. I love this, it's the greatest. But again, to be clear, like exactly what happened was he gathered all of this data carefully, he got the good data, and he ruled out all of the terrestrial sources, and then he said, well, if it's not terrestrial, it has to be extraterrestrial. Now you might say, that's just Sherlock Holmes, right? That's just eliminative induction. If you've ruled out all the terrestrial sources, then the only remaining option, extraterrestrial, is the, no matter how improbable, as Sherlock Holmes says, has to be the only available option. But the thing was, what Jansky did that makes him actually deserve the title of the originator of radio astronomy is that there are a lot of other people, including his boss at the time, who said, there's no other possible interference, let's just go home, right? And what Jansky did was say, no, there's another possible source. We have to broaden our idea of the possible sources. This could be coming from an extraterrestrial source. And what a lot of the people around him said was, well, no, it couldn't. That's ridiculous. And so what he was able to do was to propose that this was actually, that the interference was coming from an extraterrestrial source. And so this is really in a lot of ways, a very simple example of the fundamental point that I want to make, that this second part of theory testing involves taking the data that you get, crunching the numbers maybe, doing the statistical analysis, which he did when he ruled out all the terrestrial sources of interference, but then potentially doing an analysis of the way that your theory hooks up with the data in such a way that you broaden your sense of theoretical possibility and of phenomenal, and of what the possibility of what you might observe. And in this case, he decided that what he might observe might be extraterrestrial as well as terrestrial. And that's what gave us really the beginnings of radio astronomy. So in many ways, this is a very simple point, right? It gets very complicated in some ways, but in many ways, that's what I want to say, is that really what Jansky did that allowed for progress was in a way, was this enlarged sense of possibility, of theoretical possibility, but it was an enlarged sense of possibility about what the sources of the interference could be and about what he should test for. And that's in some ways very simple and in some ways very complicated. So his hypothesis that it was extraterrestrial required him to relate his knowledge of interference on phone lines as a process to his knowledge of the possible sources of interference and their parameters, right? So one of the things that he realized was that the source of interference that he was looking at had to be much bigger and much more steady than a thunderstorm. His knowledge of the physics of interference allowed him to establish the relation of that knowledge to the phenomena and to determine the possible phenomena that would be observed under different assumptions about the source of the interference, right? So this is really, essentially, he built what Koberinski calls a generalized framework, right? So he said, look, let's take the theory that we've got and enlarge our space of possibilities about what we might observe given that theory. And so in fact, he built another theory. But he did that by enlarging his space of possibilities. Okay, so that's the first example. What's the second example? Second example is more contemporary. How am I doing on time? Sorry. Good?
Good. I would say still at least 10 minutes or so.
Okay, great. Okay. So the second one is relatively simple as well. So this is the Hubble tension. So this is a contemporary. I may be in right under the wire because this could get resolved like now. This is very close to being resolved, but it's a tension that I think I'm fair in saying still exists. So this is the Hubble Space Telescope, which looks a bit like a tin can. I shouldn't say that, but the Hubble constant, simply stated, measures the rate of expansion, Gesundheit, of the universe. And there are currently two different ways of measuring it. One is the Hubble Space Telescope, which measures distant objects like stars, supernovae, that have known brightnesses. And since they have known brightnesses and we know approximately how far they are, we use distance ladders. I say we, but astronomers use distance ladders, and they can find the distance, and that allows, then you can find out enough to calculate the Hubble constant using this data, right? So these are some of the supernovae and Cepheid stars that have been observed, and then these are used as one basis for measurements of the Hubble constant. There's another way to measure the Hubble constant, and that's to measure the cosmic microwave background radiation of the universe, or the baryon acoustic oscillation. This is just two different ways of following basically the same methodology. And if you can measure the cosmic microwave background, you can establish a cosmic ruler that defines a scale using which the Hubble constant can be measured. And this is just basically two different ways that astronomers can measure the Hubble constant, right? All details aside. Here's the Hubble tension. The two estimates of the Hubble constant do not agree. There's actually a really significant difference. It's not just, within 1% or something. It's like 9% difference. It's quite different. So the data is in. This is, again, an example of what I've called step 2, or part 2 of theory testing. Got the data in, but it's not clear which measurement, if either of them is correct, right? It should be called the Hubble puzzle, right, in a way. The problem is to figure out the solution, right, to figure out what's wrong here, right? Now, really interesting point, what's wrong is not that there's insufficient theory-level justification for the Hubble constant, right? Pretty much all of the resistance to that, including from Einstein, as we all know, is gone. And it's that the measurements of the constant are not consistent with each other, right? We've got two ways of measuring the constant, and they're not consistent. It's very unlikely that the problem is measurement error, right? That could be right, but what we've got here is like so you saw on this slide, right? There's tons of these measurements. They're all done by highly competent people. They're replicable, et cetera, right? This is very, very unlikely that we're talking about measurement error. It's much more likely that the problem is hiding in the way one or both of the estimates are derived. The theoretical framework, or the data analysis, or how theory and data are related, or the measurement process used, not measurement error, but like how we chose to measure the constant, or how we chose to measure brightness or distance or something like that. And so what most people, I think, believe to be the case is that there's something about the way that this is set up, right? The way that these measurements are set up, the way that they're compared to each other, and so forth, where there's some kind of discrepancy hiding. And what's interesting is that this might be a really interesting discrepancy, right? Because it might point to a different way of setting up the theory of one or the other of these things, right? Of either cosmic microwave radiation or of distance measurements. And it could point to really interesting problems or really interesting suggestions about how to develop the theory or how to generalize the astronomical methods. So notice in the case of the Hubble tension, you can do the following things all day without resolving the problem. You can get more data. This will not help. You'll just get more and more and more measurements that are still inconsistent with each other. Analyze the data statistically, right? I mean, there might be, actually, I should just say, analyze them just in terms of whether they whether the data actually supports a particular measurement, right? So a deeper statistical measurement might well give us a lot more information. But resolving the problem requires analysis of the data with respect to theory, but not just post-data analysis where we see does this data bear out one or the other hypothesis. We need to go deeper and look at how the data is related to the theory, to the measurement processes, to the way that everything is structured and fits together. So scientists are going to need to develop sophisticated counterfactual knowledge about the kinds of data they can gather under different conditions, using different measurement processes and data analysis. What would the world look like under different assumptions? So that's really the basic question. And to me, that's a basic question about theory testing. What kind of observations can you make under different assumptions, and how do you compare theoretical frameworks to each other in that way? So just to sum up, in my view, there are two parts of theory testing that are both equally important. One is the classic account of deriving hypotheses from a theory and gathering observations, perhaps through experiment. And the other is part two, establishing whether existing data is consistent or inconsistent with the theory or hypothesis. Okay. Now, the second part is recognized. Kuhn recognized it in his measurement essay. Duhem recognizes it. Deborah Mayo recognized it, right? There's tons of people who recognize this, but it is less often sort of discussed explicitly as a part of theory testing. And in closing, I just want to say something about one of the reasons why, which is that if we recognize this second part, which I think in some ways like we just have to recognize that this second part is part of theory testing. But if we do, and if we really follow out kind of the consequences of that recognition, we have to recognize that theory testing often isn't over when we think that it is. We don't finish testing a theory when the experiment is over and the data is in and we've crunched the data. It keeps going, right? And this is kind of potentially disturbing, that this is not when theory testing is over. So we might have thought that the test of the Hubble constant was over when we had a statistically well-confirmed measurement of the constant, right? That's part one. But now we have two statistically well-confirmed measurements of the constant, and now we have a problem. So that's part two. We have to figure out how do these measurements relate back to the theory and how do we solve this puzzle, right? So the fundamental idea really is that a test is not over just when the data is in and when the statistical analysis is finished. The data in this statistical analysis may be just the beginning of a long process of figuring out the structural possibilities of the theory, for instance, which phenomena would appear under different theoretical assumptions or empirical constraints. And this is actually how a lot of scientific reasoning goes, if you look at, especially in fields like cosmology, for instance. We can say that knowledge of mathematical principles is crucial to this process, which I think is true. We can even say that we need to know which principles are fundamental to which inferences. And so this is what I take from the Marburg School, right? We need to know what follows from what in order to make these kinds of structural judgments. None of that requires us to commit to a fixed a priori, right? Which is also fine with the Marburgers. So the answer to when is testing over is theory testing is never really over. This is my kind of disturbing conclusion for today. It's always possible to find a new way to investigate a theory, even using existing data, to challenge a theory, even using existing data. From the perspective articulated today, data we can use to test theories isn't limited to the results of experiments explicitly intended to test the theory. Even existing data can be used to test a hypothesis, build a generalized framework, rule in or out a set of possibilities, or determine constraints on the target system. And expanding on the second part of testing, then I'm done, what to do after the data is in, is crucial to accounting for what actually happens in theory testing. So a unified account of both parts of testing can help us understand episodes like Jansky's building the first radio telescope and the Hubble tension. And I will say, expanding on general frameworks is a step forward. I see this as kind of defining the problem, but obviously filling in methods of solving the problem is what needs to be done. But what I see myself as doing in this work is just sort of laying out what the problem is and how we might start to look at solving it. Sorry, thank you.